And today we will continue with interaction between the electric charges, how to charge attract or repel each other, and we are going to try to explain this. We learned that two charges repel or attract one another depending on the type of the charges. We learned that like charges repel one another. Positive repels positive. Negative repels negative. But unlike charges, attract one another. Yani negative attracts positive, positive attracts negative. In fact, interaction between two charges are very similar to interaction between two objects in space. We studied in chapter 1, section 3, gravitational force. So two charged objects near one another exert a force in each other called electric force. And in chapter 1, section 3, we learned that two masses close to each other attracts one another with a force, which is called gravitational force. And we learned that this gravitational force is directly proportional to product of the object's masses and inversely proportional to square root distance between the masses. And we calculated the force between these two objects by using the equation Fg is equal to capital G, mass 1 times mass 2 divided by r squared. And in here, G was the universal gravitational constant. It was a constant number, 6.67 times 10 to the power negative 11. So charges are also interacting in a similar way to gravitational force. But only difference is that gravitational force is only attractive. But electric force is both attractive and repulsive. How? Positive and positive repel, repulsive. Negative and negative repel, repulsive. So these two are repulsive forces. Positive and negative, negative repel, repulsive. But the force between negative and positive is attractive. That's why we say that electric force or electrostatic force, sometimes called electrostatic force, between two charges, similarly to gravitational force, proportional to product of the object's charges, not masses, and inversely proportional to square of the distance between the charges. Equations are also similar, but only difference, as I said, is gravitational force is only attractive, mass of two objects always attract one another, but electric force is both attractive and repulsive depending on type of the charges. Look at the equations. Equations are also similar. This is the equation for gravitational attraction, which is Fg is equal to capital G mass 1 times mass 2 divided by r squared. And attraction and repulsive force between the two charges are also similar to that one. Only difference, instead of mass 1 and mass 2, you are going to write Q1 and Q2, which are the charge of the particles. Here we have capital G for universal constant. In electric force, we have K as universal constant, which is 9 times 10 to the power 9 Newton meter square per coulomb square. So equations are very similar. This is also an inverse square law. Inverse square law, just like the universal law of gravity. So electric force or electrostatic force between two charges. The equation of the electrostatic force between two charges is also inverse square law. This law in physics is known as Coulomb's law. Coulomb's law. So the name of the scientist, I think surname of one of the scientists who did so many experiments about the electricity is Charles Coulomb. His surname is given for this equation. So electrostatic force between two charges can be calculated by the equation K Q1 Q2 divided by r squared, very similar to gravitational attraction between two masses, which is capital G m1 times m2 divided by r squared. All right, now let's continue. What causes or how two charges attract one another. Now we will talk about this. How do they do that? How do they attract one another? So I am going to make again a comparison between the gravitational force and electric force. Yeah, electric force is also a field force just like gravitational force. So remember, gravitational force is a field force because they don't get into contact each other from long distance. They can also attract one another, like sun attracts the earth, earth attracts the moon. There is no contact between them. That's why they are non-contact forces, which is called field force. Field force. Gravitational force is a field force. It's a non-contact force. Electric force is also field force, which is a non-contact force. A concept of the field is a model that is frequently used to understand how two non-contact objects exert force on each other. So field concept is for this one. Gravitational field. Now you are learning electric field. In chapter 5, we will learn magnetic field. All these field concepts explains how two objects or two things attract or repel one another without contact. So by using the field concept, we explain this. What is this field concept tells you? We know that Earth produces a gravitational field around itself. Every object produces a gravitational field around itself. And we know that these gravitational fields can be calculated by the equation. We learn capital G, mass of the planet divided by square of the radius. And when another object enters inside this field, like your body, for example, you are standing on the earth. As soon as you are standing on the earth, so earth will start pulling you towards the center by means of this gravitational field. And when your body enters inside gravitational field of the earth, your body will be started attracting towards the center of the earth. Same thing happens in electric forces as well. Every electric charges produces an electric field around. Then a charged object, it can be positive or negative, sets up an electric field in the space around it. When another charge enters inside this electric field, there will be an electric force acting on this charge. When a second charge object enters inside this field, so an electric force acts on this object.
Teacher, can you explain it from the part when the second charged object enters this field?
Okay, every charged object produces an electric field around. For example, here you see Q1. Q1 produces an electric field around. Yes. When a second object enters inside this field causes second object to experience some force. Very similar to gravitational field. Look at now here. Earth produces gravitational field, correct? Remember the equation, capital G, mass of the planet divided by r squared? When your body enters inside this gravitational force, your body will be attracted, correct? We learned this. Same thing happens in electric field as well. Every charge produces an electric field around. When another charge enters inside this electric field, this charge will be repelled or attracted depending on the type of charge. This is not only for Q1 and Q2. Q2 also has its magnetic electric field as well. Now, on the diagram on the left, first diagram, I showed you that Q1 produces an electric field around, Q2 is inside this electric field and will be repelled by Q1, by this electric field. Also, on the right, you see that Q2 has its own electric field as well. Q1 is inside this electric field, it will be repelled. Yani they are inside of the electric field of one another. Second charge is inside the electric field of the first charge. First charge is inside the electric field of the second charge. Yani one charge particle interacts with the electric field of the other charge particle. An electric force on each charge particle arises from this interaction between the charge and electric fields. Every charge has an electric field around. Q1 has its own electric field around. When Q2 enters inside this electric field of Q1, it will be repelled. Q2 has its own electric field around. when the Q1 is inside this electric field, it will be repelled. Yani each charge experiences a force, electric force, because of the electric field of another charge. Electric field is represented by E, capital E. Electric field symbol is capital E. This definition is going to be studied in chapter 5 as well. Same definition. Now learn this definition because you will meet this definition again in chapter 5. How can we calculate strength of the electric field? How can we understand how big an electric field is? So this is definition. Strength, yani magnitude of an electric field at a location. For example, let's say location is here. What is the strength of the electric field? What is the magnitude of the electric field at this location? Because of a charge Q. Q produces an electric field in here, but how big it is defined as, this is definition, as the magnitude of the electric force acting on test charge QO. Yeah, you are going to put here a charge in here. This charge will experience a force, and you will divide this force by test charge itself. So let's now draw it on the picture. Yes, there is a charge Q. This charge produces electric field around. I'm going to choose a point. What is the strength of the electric field at this point? This is the question. To understand that, I am going to locate this point as a test charge, QO, just locate it like this. I will locate it, a test charge in here. So this charge will, of course, experience a force. We've just learned that. Positive repels positive. If I divide this force by QO, I will calculate the electric field at that point. This is the equation of electric fields. So, and very important equation, we will talk about this in chapter 5 as well. So, electric field at any location is calculated by the electric force acting on the charge divided by charge itself, F over Q. Unit of forces we know Newton. Unit of electric charge we just learned yesterday, Coulomb. So what is unit of electric field? Newton per Coulomb. Yeah, Newton divided by Coulomb is the unit of electric field. Unit of electric field. If I insert equation of F in this equation, F is equal to, we just learned that, K, Q1, Q2, divided by R squared. If I insert this equation into the F, so then I will get equation for electric field, one more equation. F is equal to K. So first charge is Q, second charge is QO, divided by separation between them R squared. So this QO and that QO will simplify, and we will get one more equation for electric field. K, Q over R squared. So this equation is common for every electric field, common for every electric field. But this equation is only for point charges. Only for point charges. Yeah, if there's a charge, Q, at a distance of R, electric field is calculated by the equation K, Q over R squared.
Teacher, do we find the strength of the electric field of Q or the test charge?
It is for Q. It is for Q. Q produces an electric field in here, but to understand how much is this electric field, you should locate here a test charge for testing. Then you are going to calculate how much electric field is produced by the Q.
Okay, thank you.
Okay, so now let's continue. Remember gravitational field? G. And it's a planet, and we know that a planet produces a gravitational field around. Equation for calculating the gravitational field is capital G. Mass of the planet divided by square of the distance from the center of the planet. When an object enters inside this gravitational field, we know that there will be a force acting on this object, just like your body. So your mass is m, small m. Small m enters inside this gravitational field. According to Newton's second law, we can get how much force acts on your body. Only you should insert this capital G, mass of Earth times Earth square instead of G, right instead of G. That capital G, mass of Earth multiplied by, divided by R of the Earth square. Let's get it. So Fg equals to mass of man multiplied by G. G is equal to small g, capital G, mass of Earth divided by square of the distance from you to the Earth. When you rearrange this equation, you are going to get universal law of gravity. So just put M in here, capital G, mass of Earth times mass of man divided by radius of the Earth squared. So same thing can be written for electric field as well. We know that every charge, it can be positive or negative, produces an electric field at some distance, and this electric field is calculated by K times Q over R squared at any point. When a charge enters inside these electric fields, so it will be repelled or rejected by this field. So what is the equation for electric force? Electric force, we know that F is equal to Q times E. Yani E is equal to F divided by Q ohm, cross product. So F becomes Q times E. So in this case, we are going to, instead of E, I am going to write its equivalent. What is E given here? I will insert in here. So F is equal to QO times K times Q over R squared. So it's going to be the same equation we got Coulomb's law. So K times Q times QO over R squared. So their interaction, field interaction between gravitational field and the mass, very similar to interaction between the electric field and the charge. So mass enters inside a gravitational field, it will be attracted. Charge enters inside an electric field, it will be attracted or repelled. Electric field is a vector quantity, just like every field. Gravitational field is a vector quantity. Electric field is a vector quantity. We will learn in chapter 5, magnetic field is a vector quantity. And so every vector has a direction. Electric field also has direction. Electric field is around the charge is radially outward or inward depending on type of the charge. If charge is positive, just like this, electric field is radially outward. What does radially mean? Radially means on the radius. Remember, we talk about this, on the radius. These electric field lines are on the radius of this circle. There's a circle I draw. And we know that radius always perpendicular to the circle. Yani these angles are always 90 degrees. So electric field lines are radially outward from a charge along the radius. But for a positive charge, they are outward. But for a negative charge, they are inward. So look at the direction of the electric field around the negative charge. They are again on the radius, the radial line on the radius, but their directions are towards the negative charge. So we have to know this. Electric field for a positive charge is radially outwards, out from the charge, but electric field around a negative charge is radially inward towards the charge. When a charged particle is put in an electric field, an electric force acts on the particle and sets the particle into motion and accelerates it. Now you see here two electric fields. So one electric field is on the left. You see that. Positive charge produces an electric field outward. We just learned that. When we put an electric charge inside this field, this charge experiences a force. Because positive repels positive, for a positive charge, electric force acting on the charge and electric field will be in the same direction. For electric force acting on a positive charge, always in the same direction of the electric field. This is very important for chapter 5 and chapter 9. So positive charge always starts moving in the same direction of the electric field. This charge will start moving in the same direction of the electric field. But if a negative charge is located in an electric field, a negative charge is located in an electric field, because we know positive attracts negative, electric force is going to be in the opposite direction of the electric field. So if a negative charge is located inside an electric field, so force will be in the opposite direction of the electric field. So electric force acting on a negative charge is in the opposite direction to electric field. So a negative charge starts moving in the opposite direction of the electric field. So electric field is to the right, electric force is to the left. So these two are important in the perspective of 12th grade. Don't forget, if we locate a positive charge inside an electric field, there will be a force acting on the charge, which is in the same direction of the electric field. But if you locate a negative charge inside an electric field, there will be a force acting on the charge in the opposite direction of the electric field. And negative charge will move in the opposite direction of the electric field. Positive charge will move in the same direction of the electric field. So when positive charge is located inside an electric field, and electric force acts on this positive charge in the same direction of the electric field and sets this charge into motion and accelerates it. But if a negative charge is located inside an electric field, so a force in the opposite direction of the electric field acts on it, and it starts moving in the opposite direction of the electric field. And electric field sets a charge into motion. So the question, how can you set a charged particle into motion? By using an electric field. Also, we are going to talk about this in chapter 5. So one positive and one negative, if you put them close to each other, so between the charge, look at the direction of the electric fields. So from positive charge, it is outward. For negative charge, it is inward. Look at their directions. Are their directions same? Are they in the same direction at this region? Are they in the same direction? Can you see it?
No, they're not.
Why not? Look at the arrows.
Yes, they are.
Yes, they are. Yes, they are.
If two vectors are in the same direction, will they support each other?
Yes.
Yes, they will. That's why electric field between two charges are stronger. Very strong electric field we got because they are in the same direction. But away from the charges, electric fields are not in the same direction. They make some angle. That's why electric field is not so strong when you move away from the charges. And when you look at this diagram on the right, you will see that electric field starts from positive charge and terminates, stops at negative charge. So direction of the electric field is always from positive charge to a negative charge. When you keep a charge close to each other, one positive, one negative, around these charges there will be electric field, and these electric field lines are always from positive charge to negative charge. It starts or begins from the positive charge, it stops or ends at the negative charge. Okay, then I draw two circles. You see them? One circle in here, the other one is in here. Through which circle, A or B? So many lines are passing. Which one? A or B?
B.
Yes, B. What does it mean? If the lines are closer to each other, electric field is greater. Intensity of the electric field is greater. A strong electric field. Remember, we did the same thing. We talked about the same thing when we are talking about the sound intensity. If the sound rays are closer to each other, so sound intensity is greater. Same thing happens in here as well. If electric field lines gets closer to each other, electric field is greater. So that's why in this region, say that electric field is in E1. In this region, say that electric field is E2. So E1 is greater than E2. The high density of lines between the charges indicate a strong electric field. Intensity of the electric field is greater at the location where the electric field lengths are closer to each other. Clear? Any questions? All right. What if charges are like charges? One positive, another positive. Look at the direction of the electric fields in here. Are they in the same direction?
No.
They're opposite. Opposite vectors, what do opposite vectors do? What do? They cancel each other. If they cancel each other, what happens to electric field? It becomes zero. So if two opposite charges are held close to each other, two like charges, positive and positive, electric field between these charges becomes zero because their directions are opposite. That's why they cancel each other. So if you want to get an electric field which is stronger, you should keep two unlike charges close to each other. So because electric field between the charges gets stronger. But if you want to get a weak electric field, so you should keep two like charges close to each other because electric field between these two like charges cancel each other and net electric field becomes zero. All right, so now there's a problem I'm going to solve, then I will finish the course. This problem, normal electric field problem, but we are going to solve a very similar problem about the magnetic field in chapter 5. Only concepts are different, numbers are different, but logics are the same. A charge, Q1, 5 microcoulomb. Microcoulomb is unit of charge, just like coulomb, but like meter, micrometer, kilogram, microgram, or something like this. And 1 microcoulomb is equal to 10 to the power of negative 6 coulomb, and you will meet in chapter 6. So you should know this. 1 microcoulomb is equal to 10 to the power of negative 6 coulomb, just like every micro. So Q1 is 5 microcoulomb, and a second charge is Q2, negative 3 microcoulomb. One of them is positive, the other one is negative. Are separated by a distance of 0.8 meter. Find the electric field at a point P between the charges, which is 0.5 meter from Q1. So now I'm going to locate charges. Q1 is positive, Q2 is negative. I located Q1 positive as a blue, Q2 as red, which is negative. And separation between these charges are 0.8 meter in the questions given. I wrote here 0.8 meters. Find the electric field at a point P between the charges, between these two charges somewhere here, but where? 0.5 meter away from Q1. So I will choose a point P, and this point will be 0.5 meter away from Q1. So what is a net electric field in here? At this position, both charges produces electric fields. We know for positive charge, electric field is away from the charge. For negative, it is towards the charge. We just learned that. For that reason, at the location of P, at this point, both charges, Q1 and Q2, produces electric field. Q1 produces an electric field to the right. Q2 also produces electric field to the right. Look at their directions. So, for Q1, electric field is outward, which is to the right. For Q2, electric field is inward. It is also to the right. Electric field, because of Q1 and Q2, at point B is going to be to the right. This is E1. E1 is electric field at point B because of Q1. Let's calculate how much is E1. Equation of E1. What is equation for electric field? KQ over R1 squared. K is constant. It's given. Just the constant in chapter 5 it will be given. Q1 is also given 5 microcoulomb, but I will convert it to coulomb. R1 is given, which is 0.5 meters, so I am going to write into the equation. I will find it. K is 9 times 10 to the power positive 9 is given. Q1 is 5 microcoulomb. I converted to coulomb by multiplying 10 to the power of negative 6. Divided by distance from charge to the point, which is 0.5, but squared. When I do the calculation, I will calculate that this Q1, first charge, produces at point P an electric field which is 1.8 times 10 to the power of 5 Newton per coulomb. But second charge also produces an electric field at point P. This electric will be also to the right because we know that electric field is always towards the negative charge. That's why electric field at the location of P must be to the right as well. So let's calculate how much is it E2. It is equal to half. First, I need this distance. I need to know this distance. How can I get it? Total distance is 8. That distance is given in 0.5. 0.8 minus 0.5, it becomes 0.3 meters. So separation from Q2 to the point is 0.3. Then I'm going to use equation again, E2, take Q2 over R2 squared this time. So Q2 is 3 microcoulomb, so I will multiply it by 10 to the power negative 6. R2, 0.3 meters, just write it into the equation. And after that, calculate what is E2 is. We got it. E2 is 3 times 10 to the power of 5 Newton per coulomb. Now, what is net electric field at P, at point P, which is resultant electric field? So there are two vectors you see, E1 and E2, and these two vectors are in the same direction. If two vectors are in the same direction, what should I do? I should add them or subtract them? What should I do?
You add them.
Add them. We add them. I will add them. E1 plus E2. Let's add them. E1 is 1.8 times 10 to the power of 5. E2 is 3 times 10 to the power of 5. Add them. Result is 4.8 times 10 to the power of 5 Newton per coulomb. Okay. This is all for today. I think time is up. I think you will not have a chance to ask a question. Take care. See you.